1. Okay, and oops, there we go. And we could plug in a different number. What would you guys, we want to find a positive y value. What number might you plug in at this point? 1. Okay, so if you plug in a 1, you get 1 minus cosine of 1. And so it's interesting, like you could, I suppose, use the calculator for this, but I don't think you really have to, because cosine, if you think about it, the outputs for cosine oscillate between which two numbers? Negative 1 and 1. So cosine of 1 is going to be somewhere between negative 1 and 1, right? The highest it could be is 1, and we know that cosine of 1 can't be 1, right? Because cosine of 0 is 1. And so it's going to be 1 minus something that's less than 1. So guaranteed, even if we don't know what that number is, couldn't we say this with confidence that f of 1 is positive? We don't know exactly which positive number it is, but we know for sure it's positive. And so, yes, I would say then that our 0 would have to be somewhere between 0 and 1. We still don't have a real good sense of it, but we've at least narrowed it down to that. What would you then use as your kind of your first number? Totally up to you. 0.5. 0.5, all right. So that means our first guess is going to be 0.5. I'll just put guess 0.5, and let's use Newton's method. So since Newton's method does come from something pretty simple, you know, the point slope form of a line, be something I'd want you to remember on your own. So let's see if we can write it down. I think the way I presented it to begin with was x2 equals x1. Were those I used those subscripts? And then is it minus or is it plus? It's minus. And then what goes in the top of that fraction? F of x. What goes in the denominator? F prime. So f of x up there, f prime of x down there. And so we could formalize this for ourselves to make it a little bit easier. We could say then that the next x coordinate equals the previous x coordinate minus f of x, of course, is x cubed minus cosine of x. And then f prime is 3x squared plus sine of x. So that'd be our little formula there. And we'll just run our hopefully increasingly accurate values through that formula. So this would be where we break out the calculators. And we get to suspend your disbelief a little bit because, yes, you could just use the zero finder, but we're trying to talk about where a zero finder could come from. So let's plug in that 0.5. So that would look like this. x2 equals 0.5 minus f of 0.5 over f prime of 0.5. Whoops, there we go. So you run that through your calculator, and what do you get? I have no idea.
I got 1.1121.
1.1121? Okay. And as we did you guys get something different?
That's what I got.
1, 2, 4, 5, 6, 7.
Parentheses issues, maybe? You got the same thing, Cameron?
Yeah.
Yeah, I got it. 1.11214.
So did you see in the video how I took that whole value and tried to store it? So I can't remember if I showed that to you in the video. You store it as like alpha A or alpha B or whatever. So go ahead and store that so you don't have to rewrite the whole thing out. And that'll become our next x1. So I'm going to, I don't know how well this will work. I'm going to attempt to erase that. Well, no, actually that's not what I'm going to do. I'm going to say 1.1211, and I'm going to say that that's going to be my alpha A. So that's one iteration. And we can see, do you guys all agree on the 1.1211 thing? We all do agree on that? Okay, fair enough. You can see that that's like out of the realm of possibilities, right? Because we decided, hey, it's got to be between 0 and 1. It should tighten up quite a bit better here in a second. So let's try that. So we would go x2 equals that A value minus f of A over f prime of A. This is iteration number 2. So when you retry that, what do you get?
9.0967.
Whew, 9.9.
0.9. Oh, sorry, 0.90.
0.9. I was going to say we're going the wrong direction. 0.9.
Yeah, 0.909.
So I'll just put 0.909 ... I would store that again as either alpha A or alpha B, whatever you choose. And then we'll try to run it one more time. I'll come over here and do that. So for the final time, x2 would equal b minus f of b over f prime of b. And that would give us, did you get it, Lenny? No? Are you calculatorless today?
Yeah, I took it out for the SAT this weekend.
Oh, SAT this weekend.
I got it, yes. 0.86726.
0.86726. How you guys feel about that? Okay. So that's right there in the middle of the possible realm, right? 0 to 1. We decided that was realistic, and so that's right there about where we would expect 0.86726. It did say 3 iterations. Obviously, we could run 4 or 5 or 10 or 20 or 1,000, but 3 maybe is good enough. Did you guys compare this with what your calculator spit out for a 0, like a 0 finder? Should be pretty close. It doesn't take too many cycles to get this close.
It took 6 iterations to get it to
The same as
just
with...
6 or 7 decimal places out.
Okay. So you got...
Yeah, I didn't write it all down. I just did it on my calculator.
Okay.
So you
Yeah,
got
no.
0.8654754.
Is the actual.
Okay, so we're accurate to the hundredths place right at this point.
Yep, and then on number 6, I got to the 474.
Got it. Got
Right
it.
out there.
Okay, fair enough. Fair enough. You guys seeing that right now we're pretty accurate, but I mean beyond that second decimal place we differ from the calculator a bit. Okay, so does that work? That makes sense to you guys? Okay, so I want to present a couple of other, and I don't remember how much room I gave myself here, so forgive me for doing this. I'm going to erase that. I'm going to just kind of squeeze this at the bottom and just find a little bit of space. I thought we'd mess around with this a little bit more. Let's see here. Let's do this. I hadn't planned on exactly doing this, but let's do it this way. Let's try to do this totally independently. Like I know that we normally kind of work together and compare and all that. Lenny, I got a calculator you can use. I think I got it in my bag. But why don't I give you a different equation and just you start from total scratch using Newton's method. Let's do the 3 iterations thing. It's kind of a standard for us. So let me give you this equation right here. Y equals 1/3 x cubed plus x minus 10. So use 3 iterations. You decide your domain of realistic possibilities, and then obviously you decide your initial guess off of that. But I want you to try to do this as independently as possible. So let's see here. What did you guys say? You tried out 1 and 3? No, you tried 0. F of what was the first one? 0? Okay, so f of 0 seems logical. F of 0 is -10. F of 3 was 2. And so the reasoning that we used was since f of 3 is a little closer to a y value of 0, that maybe our guess should be a little closer to 3. So 2.5, right? I'm just trying to trace through your logic. I think it's good. Okay, so our first guess is going to be 2.5. So we start using Newton's method. X2 is equal to 2.5 minus f of 2.5 all over f prime of 2.5. And when you guys ran that first cycle, so Caroline, Darian, you guys started the same number. Others used 2.5, I think. What'd you guys get? Caroline, why don't you share just maybe briefly approximately the number you got?
2.816.
Okay. ... and then store it as maybe a or something like that. So then our next cycle would give us a minus f of a over f prime of a. And so then when we reran that, Darian, what'd you get?
2.7869.
2.7869. ... Other stuff, we store that as maybe a different value. And then finally we get to our final. Oops, that should be x2. There we go. B minus f of b all over f prime of b. There we go. And that's where we got. And Caleb, did you agree? Do we all agree kind of when we, this is where I'm kind of curious to see what happened. Caroline or Darren, why don't you share what you got for kind of your final approximation?
I got 2.78667.
667. So I know all you guys started with a little different. You didn't start with 2.5. It was like 2, wasn't it?
Mhm.
So where did you end up compared to that number on that third iteration?
I got 2.7868.
Okay. So just a slight difference, out there to the 10,000th place. You started at a slightly different spot. I don't think that it would take too long for us to all agree eventually on what that would be. Okay. We good? Okay. I want to show you maybe a couple more things here. So bear with me. Let me erase this again. Apologize, I didn't give you a whole lot of space to do all this stuff. So there are some potential issues with Newton's method. So let me show those to you. Let's say that this first one. Sorry, McKenna, go ahead.
I was just, if you have to use this, will it always say like use Newton's method in
Yeah.
the instructions? Okay.
Yep. Yeah, if I want you to use Newton's method, I'll just come right out and say it.
Okay.
Otherwise, yeah, because why wouldn't you just use a zero finder?
Yeah.
Yeah. You're welcome. Okay, so let's say this is kind of silly, so just bear with me here. Let's say we had something like this. Y equals cubed root of x, also known as x to the 1/3. You can just kind of tell by inspection where the x-intercept is. When x is 0. Okay. But we'll still use this to illustrate how Newton's method can potentially go wrong. So you need to be aware that that's possible, that it's not a perfect thing, that depending on the nature of the function and the value that you choose and kind of how it corresponds with the function and certain key features of the function, you could have an issue. Okay? So let's say we were just feeling real clueless and we didn't recognize the 0 right away, and we're like, let's try 1. Just cuz. Let's just try 1. Let's see what happens if we use Newton's method with 1 as our initial guess. So we would write x2 is equal to 1 minus f of 1 over f prime of 1. And of course, that would represent the function f of x, I guess. And then, so y prime would be 1/3 x to the negative 2/3. So take a minute, and will you guys find what that would be? Use your calculators. Let's see here. I will try this. I chose 1 because the cubed root of 1 is convenient, right? Let's see if we try 1. Is it negative 2?
I got -6. I got -2.
I tried to do it real quick in my brain, which sometimes works great, other times not as great as I hope. So -2?
Yeah.
Okay. All right, well, that's not unheard of, right? Remember that first one we did? We decided the 0 had to be between 0 and 1. The first number we got was 1.211, so it's like, or 1.1211 or whatever. This is not like a really alarming result yet, but watch what happens when you try it again. X2 equals -2 minus f of -2 all over f prime of -2. Probably be a little easier if you simplified like that fraction, if you just simplified it in general. And that's what I just did. It makes it a lot easier. So it's -2 minus -6, right? So it ends up being +4. So I must say that that result is a little alarming because we know what the answer is supposed to be. It's supposed to be 0. But now -2 is like maybe a little off the beaten path. Now 4 is even further away from what we know it to be. If we do it one more time, we'd say 4 minus f of 4, all over f prime of 4. What'd you get? -8. So, I mean, this is kind of an interesting pattern here. It's geometric. It's like a alternating geometric. You know, it goes 2, 4, 8. What would you guess the next one would be? Positive 16. You can see a pattern emerging here. And the pattern is a little disturbing because we know the answer is supposed to be 0, but we are definitely not headed for 0. And so this would lead you to think, well, gosh, I don't think Newton's method works, at least not in this particular situation, right? So the question I think that we could ask right now is Newton's method just not suited for this function? Is the function the problem? Or is our guess of 1 kind of the culprit as to why it's not working? Because you've seen 2 times and in a variety of ways already that it can work, right? So what's the problem? Do you think it was the 1, or do you think it's just this function, there's just some issue with this function? I don't know. You just want to go with that? You don't want to investigate any further? Let's do this. 1.5 didn't work? But what if we did like a fraction between 0 and 1? Because we know the answer is supposed to be 0. So what if we did, like 0.5 or 0.25 or something like that? If the culprit earlier was 1, maybe if we had a little better guess to begin with, maybe that would be better, you think? Why don't you try it? Try a couple of cycles. Does that help?
No.
What'd you try?
0.5.
0.5 is just gets worse and worse and worse, kind of like this one did?
-1, 2, -4, 8.
So starting to see the same pattern emerge. So maybe it's just this particular function, or maybe there's something else interesting going on. Maybe we should, it is this function, by the way. That is the culprit. But let's go a little deeper. What is it about this function that's giving Newton's method fits and problems and making it not work? Have you looked at the graph yet? Why don't you look at a graph? I'll erase all this work here because none of it's going to really help get to an answer that we already know. I won't erase that stuff. What does the graph look like? The graph of cubed root of x.
Just sideways x cubed function.
Sideways cubic, right? So something is going on right there at 0.
How's a vertical tangent line?
Ah, there it is. Don't we have a vertical tangent line, which I am attempting to sketch? There we go. Don't we have a vertical tangent line right there at 0? That's what's giving Newton's method so much issue, right? Because when you start dealing with y prime, and we're trying to like narrow in on 0, what is y prime going to start doing in this case as we try to get, it's going to be like, whoa, I'm heading towards infinity. And did you notice how the values are getting boom, 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 further and further away from 0? They were alternating, granted, but it was like, it was 2, -4, 8, -16, or what, I'm flipping the signs around, but you get the idea. We're getting further and further away from 0 because that slope of the tangent line is actually heading towards infinity in this particular case. So the problem is the function, and the issue is the vertical tangent line that we get right there. Okay, make sense? Okay, can I give you one more example of where Newton's method could go bad, kind of like this one, but it's a different scenario? Okay, so let's do this. I apologize. As I was looking at the notes, I don't know, yesterday, the day before, thinking about what we were going to do today, I was like, for all the stuff I'd like to do with them, I didn't give them enough space. So do a back of a page somewhere, or whatever. Go with your own paper, whatever you want to do. Or you just kind of mess around with this one. Let's say that we have f of x is equal to cosine of x. No. Let's do sine of x. Sorry. F of x is equal to sine of x. And again, we're going to be silly here because we, just pretty quickly we'll know the zeros of sine. That's not the big issue. That's kind of the point here, though. We're trying to use something that we know to illustrate a potential problem with Newton's method. So let's see here. Here is my attempt at a graph. sine of x, right? Okay, so let's say that we were looking for zeros. You did a few test values. You plugged something in. Maybe I don't know. Let's say you plugged in. Who knows why you do this? But let's say you plugged in like 3 pi over 4, and you found out that that was a positive y value. And let's say that you plugged in, I don't know, negative 3 pi over 4. Maybe you were partial to those parts of the unit circle, and you found out that that is a negative y value. And so you thought to yourself, somewhere in between, you could have picked 0. Who knows? Obviously, that would just be the perfect guess. But let's say that for some odd reason, again, and we're suspending our disbelief a little bit because we all know what the 0 is. Let's say that you arrived at some conclusion. You thought, you know what I'm going to do? I'm going to pick pi over 2 as my initial guess. It is in between those two. And so, if you think back to what we did, remember the third one we did where I just threw it up there. We didn't decide together on a guess. Some of you picked 2.5, others picked 2. I suggested 1.5. And so, somebody could look at this little domain here and think, yeah, pi over 2, that's a reasonable guess, right? So let's think about what would happen if we did Newton's method. We would say x2 is equal to pi over 2 minus f of pi over 2. Oh, you already see it? Over f prime of pi over 2. And so with that guess of pi over 2, what immediately happens?
It's an error.
Error. Why is there an error?
Divided by
Cosine is the
pi over 2.
Yeah, because the derivative is cosine, and cosine of pi over 2 is?
0.
So you end up with something over 0. So your calculator freaks out, as it should, and you freak out because you're like, oh, I thought this always worked, or most of the time worked, but it doesn't seem to be working. In this case, the problem is not the function. The problem is the guess, right? The problem is the guess. If we were to say, you know what, pi over 2, and the point, of course, is that pi over 2, you've got the horizontal tangent line thing going, and that's going to cause a 0 in the denominator. It's going to cause the calculator to freak out because you can't divide by 0. Maybe instead of choosing pi over 2, if we chose pi over 4, pi over 6, pi over 3, something better, it would work out just fine. Okay, does that make sense? So in this case, the problem was the guess. The other one, the problem was the function because of the vertical tangent line was where the 0 is. Okay, so what do you guys think? Newton's method, pretty good, not perfect. Sometimes it'll fail. Other times it works great. But I wanted to give you some insight into that and a little insight into how zeros can be calculated. I think back to you guys in like Algebra 2 or pre-calc. Remember the rational roots theorem? I look at this and I'm like, this is a million times better than the rational roots theorem. Remember all that stuff you had to do? Like factors of the last divided by factors of the first. And sometimes your list is like this long and you're like, all right, here comes synthetic division on steroids. And you just go synthetic division. And like on the 6th one, you're finally like, are you real? Remainder 0? Yes. And then you can finally break it down a little further. This one, it's just like a couple, we're talking about decimals versus exact answers. I get that. But as far as being able to approximate answers, this is really, really quick, especially if you can program your calculator. It'd be over with as soon as you can push the buttons and hit enter, right? Cycle through, boom, answer. And so potentially a useful, fun method, but something that you just haven't seen before. That'll be fun. Good? Okay, cool. I had fun thinking about doing that with you guys, and you guys obviously get it. Okay, so we're going to do a little bit of work here in 3.5, I think it is. So let's go back a little ways. And by the way, most of, I just call it like our extra material or our bonus material is kind of like that, to be honest with you. I'm certainly not going to make that a major sticking point. I hope that us spending, about 40 minutes on Newton's method, you feel real comfortable. And reading your faces, you look comfortable. Look like you came in the room relatively comfortable. So that's great. So as you think about some of those other later things, I'm going to definitely make it as palatable as possible. I'm not going to be like, let me set the bar so high that this becomes something they lose sleep over. I just want to give you a taste of it so that when you're in Calc 3 or whatever later on and your teacher refers to, first order linear differential equations, you're not like, what? You're like, oh yeah, we did that. Or if they refer to Newton's method. Now I think at this point, you'd be like, oh yeah, I think I can remember that and I could probably do it. Instead of like, oh my gosh, one more thing I got to remember. That's kind of the point. That makes sense? So I hope you see that as like a service to you as opposed to just like one more thing on your plate. Okay, so limits at infinity are what we're going to discuss here, and we'll maybe get through a little bit of this here. 3.5, tomorrow is 3.7, and we'll be rapidly finishing up this unit, right? By the end of the week, we should be easily finished. One thing I would say as we move into the end of chapter 3, if you guys would, like we still definitely have a couple days, but if you guys would print out the chapter 4 notes, we'll be getting into that soon. I'd rather you just have that kind of tucked away in your notebook. So if we go a little bit faster than I thought, we'd be like, all right, let's do chapter 4 real quick. I'm always a fan of being ahead because there's always going to be one of those days, right? Either a snow day or Valor's like, you know what, let's just not have school today because it's Maya's birthday, or, who knows, right? Yes. Who knows what it might be. And so I'd rather be a little bit ahead than a little bit behind. So we'll just keep plugging away. All right, so limits at infinity, these are limit as x goes to infinity of f of x, or limit as x goes to negative infinity of f of x. And so these are good descriptors of horizontal asymptotes, the extreme ends of the functions. And so the graphs there are good illustrations. So if you look at the graph on the left, if we were to, the green graph, if you were to say, hey, limit as x gets really, really huge to the right, just based on the graph, I mean, this is a far from a perfect method, what would you guess that would be, that limit? The one on the left is what I'm talking about. -2, right? You can see that dotted line is supposed to probably represent a horizontal asymptote. That's typical. And so, yeah, it looks like the green graph is kind of cozying up to that. Long term, we'd say, yeah, it's probably headed towards a y value of -2. And then the one on the right, as x approaches negative infinity, limit is x goes negative infinity of f of x. Again, what would you estimate from that picture?
4.
Boy, I don't know if it's just my eyes, but yeah, I'm having, the boxes are all over the place. Is it 4? Okay, so equals 4. Whoever wrote these notes should make those boxes a little bigger. Okay, so does that make sense? Long-term behavior. We're talking about as x gets really, really huge to the right or really, really tiny to the left, right? Negative infinity far left. And we're looking at the long-term behavior. So some real basic rules I want to make sure that we are solid on, because this will be the basis of a lot of what we do. Really, honestly, gosh, now that I think about it, a lot of what we do, even moving into second semester, these two little rules right here, limit as x goes to infinity or negative infinity of c over x to the r, these are really crucial rules that we just have to know perfectly. So c stands for some constant, and x is some polynomial-ish kind of thing with an exponent, right? So what would you guess the answer to the first one would be? Constant numerator, denominator getting huge.
0.
0. Yep, 0. And so we can dive a little deeper into that if you want. I can draw a better 0 than that. There we go. What about the other one? C over x to the r. X is getting really, really huge, but in the negative direction. What would you think that would be?
This will be 0.
Still would be 0. Yep, still would be 0. There we go. So here, let me give you just an illustration of that. So if we looked at kind of a classic function, y equals 1 over x squared, doesn't 1 over x squared pretty well fit the c over x to the r pattern? 1 is a constant, just like the c, x to the 2, just like x to the r. Does that make sense? Okay. So in a case like this graph looks like that. The other part looks like that. And there you go. So if you think about x heading to the far right edge of the graph, boy, that's not what I was expecting. How about that? So x is going to the far right edge of the graph. You can see how the y values are heading towards 0. And then as x heads to the far left edge of the graph, again, the y values heading towards 0. That make sense? Okay, awesome. So we'll do maybe an example or two here before we go. But I just wanted to share my thoughts on infinity with you guys.